Mic test 1 2 3 4 5. Mic test 1 2 3 4 5. Mic test.
हेलो हेलो हेलो, सुनाई दे रहे? हेलो हेलो।
No, it's not.
No, it's on. You start?
Yeah.
Good morning and namaskar to you all, and a warm welcome to all the audience, both who have joined us physically online, as physically, as well as those who are my colleagues from Indore, Bombay, and Kolkata, who have joined us through the online platform. It's a privilege for us to host Professor Raychaudhuri to give us who's giving us a talk on various things, and I'd like to introduce the audience to him. We have our students, our staff. We also have our collaborators coming from different colleges and different the institutes, and we will also be joined by some of the undergrad students from Bethune College who have been doing their NAB internship with us. So, sir, is going to be a very wide audience which actually matches the wide exposure that you have. And it would be very blasphemous of me even if I try to attempt to introduce the Professor Raychaudhuri, for whom we say the subject knows him. So we request Professor Pal to kindly introduce Professor Raychaudhuri to our audience. Professor Pal.
Good morning. Thank you for requesting me to introduce Professor Raychaudhuri or Raychaudhuri. It's my honor and privilege to do so. I don't need a piece of paper to introduce him. So, but since there are undergraduate students and others who are from outside the institute, so maybe it is customary to do a kind of formal introduction to Professor Raychaudhuri. So, Professor Raychaudhuri is a condensed matter physicist and material science. Truly a researcher, experimentalist, along with theoretical background. So his research mostly on large domain like physics of tension, nuclear oxides, perovskites, room temperature physics. Name anything on experimental physics he has done. And he's a Shantishwar Bhatnagar Prize winner, fellow of all science academies. PhD from Cornell, and that made him a care. So, and then later he moved to Max Planck as an Humboldt fellow. His career at IST, was a director at NABL, Delhi, and also at SMU Center at Kolkata. And the important thing that in my opinion, is that he produced very good branch of students who are now faculties in Indian science, and they are doing extremely good. So he has just kind of a three now, like Anupam Ghosh is a student, Kodipti, Shomini Kornarayan. So she recently joined as a director at Max Planck Institute, so his own student. So that's really very important for a scientist, that when we find that his students are doing extremely good in the professional life. And especially for UGC-DAE season, he has contributed immensely. He was, many of you may not know that he was the chairman of our scientific advisory committee for 2 consecutive terms. And during those periods, before I joined at UGC-DAE season, so he was instrumental in procuring different instruments, like shaping our UGC-DAE research directions as a chairman of the scientific advisory committee. And I had some about 2 years of overlap with him when he was the scientific advisory committee chairman, and I found that his suggestions in the committee was truly helpful for the consortium as a whole. Earlier he was INSA senior. At the moment he is INSA senior scientist. So when he expressed his desire to join UGC-DAE CSR Kolkata Center as INSA senior scientist, I encouraged him to do that because he had the option to go any other institutes in Kolkata, but I felt that if he joins UGC-DAE CSR Kolkata Center as an INSA senior scientist, that would be great for our institute, especially the Kolkata. So with this introduction, I request Professor Raychaudhuri to talk about a very nice topic, especially the SI index and calibration and accreditation and world trade. Professor Raychaudhuri.
Yeah. So, do you have a color mic?
Oh, so this is
Oh, this is also.
you can speak up.
Okay, good morning. And thanks to Amlan, who's like my younger brother whom I know in student days. And of course to Sandeep and the colleagues here. This talk is a genesis for, to Sandeep talking about the world trade and physical measurements. It's very disjointed thing, but will convince you that the physical measurements have a tremendous meaning for the $26 trillion world trade that goes on today in finished products and all these things. So initially, the first version of the talk was a bit more on the precision measurement. I gave it in ICTS 2 years back, that's where it started. But I thought when I was teaching in our course over here that I may have a module on just on the units. For when you talk to the students, you'll find out that the way we define kilogram or meter or a second or any physical unit is still not known. In the sense, we are still in the old background. And so I proposed this subject with Rajesh. Rajesh interestingly agreed that I should give the course, but then Sandeep came in the picture and he decided that we should have a full talk. Fine, no problem. And let me tell you that is why I am taking up this topic. For when I was searching on the physics books, some of them have come up with a bit of a newer definition of say kilogram and all that. But the most of the textbooks are still defining kilogram in the old way, in the sense like, if you allow me to speak in Bengali, when we are students, there was a Bengali book, I don't take the name, it's a very famous Bengali physics book. Almost all the students who did higher secondary at the time studied that book. It used to define kilogram like this. ইহা প্যারিসের উপকণ্ঠে গভীর মাটির তলায় লেখা একটি নলাকৃত বস্তু বিশেষ ধাতুতে তৈরি নলাকৃত বস্তু ওজন. We define a kilogram like that. You think it is almost James Bond going there and picking up the kilogram and coming up like this. But indeed, that is the way kilogram was defined. There's nothing wrong in that definition, but then everything changed. And that's why the revolution of 2018 came. And believe me, now kilogram is defined in terms of Planck constant. You start thinking, how come kilogram is related to Planck constant? But you don't go to the shop and say, Aruda, can I have 20 to the power minus 40 h by nu dot cc? Alu. No, you cannot do that. You think they have gone mad. So kilogram is still a kilogram to us, but nevertheless it has its own meaning. So that is why I just thought that we will discuss it. And let us start and see what I have to tell you. And I'm pretty sure that it may be interesting to you. So what I like to cover is just to show you that in all aspects of our lives, there's universal measurement. You like it or not, it's there. And a bit of a touch of history that it didn't occur just today, but 5,000 years of human history, particularly the Indus Valley civilization, which you call Harappan civilization, had a completely developed measurement system. Then it will come to the big part of the talk, that is the October Revolution, which adopted that all physical units are traceable to or will be defined by 7 physical constants like C, E, H, and things of that kind. So that is the way we came. So now I also know that why we need precision measurement for world trade. A little bit of an example, and then the use of in the Indian context, but it has a more or less universal model, how the unit which is made into the highest of the labs, it decimated the shop floor and its effect on the trade and calibration, and then will come how it gets international recognition, mainly through two very important conventions the international body adopted. One, the Meter Convention of 1857, and the other is the Mutual Recognition Agreement, which we signed in 1998. So these are the two important international treaty that makes our kilogram compatible to the kilogram anywhere in the world or any other unit. So let me start where I stand. If you look into the precision measurement, which comes in the domain of what we call metrology, and that is where you get the realization of SI units. SI is System International, all in French. So that is where the really the meter convention, everything started. It's in the, totally in the domain of physics, or you can say physical sciences. Like laser, these, that, everything comes over there. So it is, and then of course you have trade in manufactured good, agriculture product, medicine, software, even pathological services, everything. So, and they need a test certificate that the product have the international acceptance, and that is what is called the conformity assessment and the domain of commerce, totally in the domain of commerce. So is there a bridge between the two, that it go from something which is very pure physics to something which is completely the domain of commerce? So that is indeed a bridge, and that is what we try to appreciate today, and that is called the process of calibration accreditation, and it follows certain guidelines, international standards organization guideline, and that is what we try to do today. So let me start here just very clearly that often the two terms, metrology and meteorology, confuse people. But let me tell you, metrology is the science of measurement. That is where we talk of units, measurements, and it has three parts: scientific, industrial, and legal. Scientific is what we do, say, National Physical Laboratory and places like that, where we do measurements and set up the unit and all that. Then there is a National Accreditation Board for Testing and Laboratories, which is the NABL, and where you really translate, have a method by which you can translate to the industrial spaces. And of course, there is a legal metrology. Many of you don't know there is actually a thing called legal metrology, which is called Tol Mol Bubble in Delhi. And there, like what you see in the marketplace, the kilogram and all that can be tested, and people can be punished. But I have never seen anyone punished for having weighing. You go to a vegetable market, still they weigh with a stone. And you can ask, Dada, it's কত 250 gram. I don't know why would you measure that stone from 250 gram, but that is the culture. But anyway, let's keep it at that. But then meteorology is the weather science, and it was established in 1875 in two places, Alipur and Pune, and where it started, of course, now the Mausam Bhavan is in Delhi, and we have a flagship lab, Indian Institute of Tropical Meteorology, Pune, and this is meteorology. So just between meteorology and meteorology, I had a massive confusion, so I thought I should clear it up. Well, let me now come to another thing. When you go to the market and buy something, you look for that many of the good products have a certificate called BIS, this symbol. And BIS is Bureau of Indian Standards. This is the ISI, Indian Standards Institution before. But what is that? Let us try to appreciate it. Let us say I'm going to buy a plug. Suppose the plug is made by Apple. Let's not say that Apple. And say the socket is made by Anchor. How do I ensure that a plug made by Apple fits into an anchor made by into a socket made by Anchor? So it should be standardized. So the body in India which makes that product standardized, which you call paper standard, is done by the Bureau of Indian Standards. And if you go into the website, you see under plug and socket, there are 20 products of different kinds. And let us take the 3-pin plug. It's very clearly said how it should be, what should be its you should say the distance between live and neutral. Okay, it says the distance between the earth and the neutral and live. What should be the diameter? Everything is specified along with the material and its conductivity, etc., etc., etc. So now what happens is that I am a manufacturer of the plug and I want to get a BIS chappa on my product. So what do I have to do? So I have to measure that the distances are all right. So I have to go to a laboratory which has calibrated equipments, and the calibration is traceable to the national standard. In our country, it is NPL, and this is called conformity assessment. That what you have done is done as per the specification of BIS, and once that conformity certificate is obtained, you can hope to get a BIS chapter. And if it is not done, then you get a short coat and a long pant. So that is really a non-conformity of a product. That you wanted to go to a tailor, wanted to make a proper suit, but he gave you a non-conformity product. Just for the interest of the audience, nowadays you know that gold is also hallmarked. And hallmark is actually started, the what came from USA and UK, but BIS from 2000 in gold and 2005 jewelry gives a hallmark. And hallmark is actually quality of the gold. For those who may not know that there is a, I can show the inside here. Inside there is a BIS hallmark, then the book company which is selling it, where the hallmarking is done, and there's a number written over here. And is a 20 karat gold is 958. 958 means the gold is 95.8% pure. If it's 22 karat, it is 916. And if it is 24 karat, then it is 24K999. So that is the way it is hallmarked. That is so. When you go to a thing, they nowadays they advertise that we have a BIS hallmark and all that. So good jewelers they can give you that particular type of certificate. Okay. Now, actually, if we look into it, units and measurements are everywhere in all aspects of life. But time, since the morning we wake up, actually from the time we come to work, wake up, sleep, eat, work, and there is time. I have to look at my husband for all Calibration and all this kind of thing. And we as a country also pray to Mahakal, which is the ruler of primordial time or possible Anantakal. So the concept of time is very much in our scripture. So other than this, of course, you go to buy a shirt and you have the total, size, maybe written small, large, extra large, extra large, etc. But I know what is size I'm talking about. And I know that when I drink milk, I milk a liter of milk. But liter amazingly is still an unit for solid. You may not believe it. And I got, now it's come. You won't believe that in Bangalore, Moody is sold in liter. So what happens is that he has a liter can you put Moody into it and sell it to you. So the first time I went to Bangalore, I had a problem to understand how can Moody be measured in liter. But then of course you come to the market, you have the kilogram and all that. Any problem? It is. What's the কাজ করছেন? Oh, Europe. Go back a little bit. It could be.
Keep the sensors there.
Okay. I pointed there only. Okay, fine. But then, of course, vegetable vendor, you go buy a kilogram of this and that. And even in the matrimony market, there is a dimensional metrology. The groom is measured, the bride is measured, there is a minimum height that you should have, everything is measured. So the life has a lot of units into that. But then, if you walk on the streets and go in front of a big diagnostics lab, this is a big diagnostics lab in the area I live, like town. NABL is accredited. Below that would be 1.5 Tesla MRI, 6 Tesla CAT scan, etc. But this word NABL accredited, proudly stated there. What does it mean? See, accreditation, what does that lab do? It gives me a certificate that my blood has so many bad things. Or your leg is broken, and after an X-ray they found that all your bones are gone, etc. But how do I know that the body which certifies that product or certificate or anything has done it correctly? And that is the process of accreditation. So it's verifying the certification body's competence. And in our country, NABL, National Accreditation Board of Laboratories, actually accreditates all labs, whether it's a pathological lab or a measurement lab or a calibration lab and everything. So that there you find your NABL accreditation there. Those are parts where in academics, you also know there is a accreditation we get in NAC accreditation. And in some of the universities, when they get A plus, they flash it in the newspaper. We got A plus first time in human being or something like that. So what does that NAC do? It's a national it's a national academic accreditation council. It's just this our universities and colleges gives us certificates. So NAC tells us that the way he is giving the certificate is correct. It's not that his certificate is a fantastic certificate. They show that certain methods are followed to give that certificate, and they have the infrastructure necessary to give that certificate. Full stop. So when you get an A++, it means that you have a good infrastructure and it stops at that. Okay, now I'm a voltmeter, say in this institution, and I want to get it calibrated. You should always get it calibrated after initial year, 2-3 years after that, you should get it calibrated, and then I can find a nearby calibration lab and if we are certified, I can get it calibrated there. The nearest one is in very near to us in the ERTL list. Those who go to the college module see it, and those who want to know exact coordinate is next to Longe Vasanti Dhaba. So I think Longe Vasanti Dhaba and it's greater, so you can decide where to go when you are going with your voltmeter. Okay, let me now come that actually accreditation metrology has been part of our society for a long time. It started with the Egyptian civilization, 3,000 years back they started it. And interestingly, they have an object called qubit. QBIT. So, like I first thought that they knew a quantum bit and all that. And it was made for a black granite and it was given on the pharaoh's hand. You see, it's very way they do it. The full stretch hand of the pharaoh, then up to this finger, then the pharaoh will put his hand like this, and this is the total unit for length. And it was then marked, and then it goes around and they built the big pyramids and all those beautiful things. One of the earliest civilization was Harappan civilization, where the UNICEF standards came. And by 2500 BC, when the Harappa the civilization matured, and there are a lot of trades, then immediately interesting, this whole metrology, measurement, particularly dimensional and weights and measure came into being. And I'll give some example. This is the mass metrology, mass measurement, and you can see this is the Kutch area, this is the Gujarat area, Saurashtra area, and you see this Dholavira and Lothal. These are the very prosperous Harappan civilization cities, and when they did excavation there, they found all these artifacts. That is how the weight was measured. The smallest units were 30. These are all from ivory, 13.7 gram weight, and that was the big, they like our gram today, and they have some unit of that, but they also have fractional and multiples of that. So there's a flourishing trade came with the metrology. And if you look into our Harappan civilization, there's a unit of length was very well known there. It's called Dhanush. So it was not king's hand like other civilization. We had a unit, and a Dhanush is about 1.9 meter, and it was done in a sandstone. And you can see Harappan civilization was well known for the complete. Okay, and the one thing that Harappan civilization did was definitely the bricks, and they standardized the bricks, and this is the size of the brick, and all other civilizations at that time took the standardized brick. It's very interesting, and of course, if you know, standard bricks nowadays is very similar to the Harappan brick, but of course, their sizes are somewhat different. So this whole history is there. That is the measurement and how it came, how they are standardized, and all that. But are we all using the same unit globally? No, but there are still some countries where they drink a pint of milk, buy a gallon of petrol, they drive a distance of a mile, and weigh themselves in pounds and measure their temperature in Fahrenheit. And the most advanced economy in the world does this. But is it a good thing or a bad thing? It can bring a disaster if the units are wrong. And I'll give you one example. In 88-89, a fantastic spacecraft was sent called Mars Climate Orbiter. It will orbit around Mars, it will map the Mars, and also it will communicate with the Earth. Fantastic! But then disaster struck. It was launched in December 11, 1998. It collapsed in 1999, not even a year. Why? Let's come to that. It was supposed to last more than a decade. Why did it collapse? But their confusion of units. So it should not be like that, right? It should all use the same unit. But the conversion from English to metric unit. So that is where the problem came. So what is the lesson we learned? That we should all follow the same unit. Your kilogram should not be different from my kilogram. Your meter should not be different from my meter. And your second should definitely not be. Of course, in India, second is a stretchable unit. Some people's second may be more than some people's second. But it's a different issue. Let's not go into it. But it happens. And velocity of light is also another unit. That is where we want that it should be said. Just a little story. Just, I studied from a school which was academically very good, but in sports it was awful. So, like if we lose to a school by less than a dozen of goals in a football, we used to celebrate for we lost by less than a dozen of goals. So one day a school match was going on to one nearby school. So our goalkeeper was always jumping after the ball crossed him. So obviously we were getting the goal in. So the drill teacher was very unhappy. He was just cursing and standing there. And all that. Then all of our classmates, he went and told the teacher, sir, okay, those days now our velocity of light are calm. Our teacher didn't stop there, but the student was safe. But then you realize that velocity of light can be a factor. It's different for different people who can have very different things altogether. Anyway, but let me now come to what we all should, but it came into being. Then the meter convention of 1875. And this is another time France, if you look in the political history, was having its third democratic things and all that. And they decided that we should use the metric unit all world. And in 1875 Paris made this sign. For the 17 countries initially signed, but then it expanded. And they created a fantastic organization called BIPM, which is, the keeper of the all the units in the whole world, and they actually conduct most advanced experiments. And they also keep that Paris, and BIPM is located in Paris Rupoconte, and they do have a vault in which the standard kilogram of iridium platinum is kept. So what that Bengali book is Paris Rupoconte Matit Kavita is factually correct, but it was stated in a way that it shouldn't have been stated. And they also give us the universal coordinated time. Nowadays we don't use the word GMT, Greenwich Mean Time, we use UTC. So what they do at touching. So this is where it starts now. And now this meter convention has 67 member states, 37 associate member states. But interestingly, not all the countries in the world are a part of it. Okay. Now let us see, they also publish a fantastic journal, scientific journal called Metrologia. That's the best journal in terms of precision measurements. Okay, now let me come to this part and first talk about the precision measurements, how the units are realized. Then let us come to the October Revolution 2018. And you know that what happened in the 1917 October Revolution, the Tsarist system was over and the Soviet system came into being. So in the October Revolution of 2018, the old artifact-based measurement unit was abandoned and things based on physical constants came into being. So let's see what happened. This is the famous standard kilogram. It is called the International Prototype of Kilogram (IPK). It was made in 1897, and it is still, IPK has its own place. And there's a meter bar on which there are two marks which actually tell us what is the meter. Now, but what happened is that the decision that is taken that we should not have these things, and then we should have a physical based system. So how does the system looks like now? There are 7 basic units. What are they? Kilogram, mass, meter. क्या हो रहा है भाई? Now, just no, go back. You have to go back and want the pointer to work on. Not working. See, you have kilogram, meter, second, ampere, Kelvin, mole, candela for radiation. These are the 7 basic units, and they are related to the 7 physical constants. So, velocity of light. This is the hyperfast transition of cesium for time. Planck constant and Avogadro constant, candela, and Boltzmann constant, electric charge. Every other unit comes from that. So let us look into it. what are the values that have been adopted? So the values of H is now fixed at this. I can see these are actually measured value for years of measurement. Now you see that they have no uncertainty. Why? But if the starting point you have uncertainty, then you exactly don't know when you are converting the into some calibration how the uncertainty will come. So you decided that this is the value, there is no uncertainty. But now you have a very good researcher who said I'll improve it. So only way you can improve it that you can add one more digit after 5. And then you said that E has been fixed. See the number of digits, 9 digits after the decimal. So if you are a good researcher, say I do a fantastic measurement of E. Boy, you have only one place left. You can only add it 10 digits. So you can imagine. So now what happens is that when this before the revolution came in 2018, a committee was set up for the core data, which looked into all the fundamental constants, how they are measured, what the values will be. It was set up and it is available in Methodologia. It's a very worth reading. It's a 4-5 page article, but how these constants were determined and what the value should be taken and all that. And it's a fantastic piece of document for the human history. So let's now see that what are the other units. Suppose there are other units, they are all derived units, like Newton. Newton, we know that it has kilogram meter per second. Pascal is Newton per square meter, so divided by meter square, it minus 1. Joule is kilogram meter square minus 2, for it is energy, mass into velocity square. And what is per unit time, so one more time in the decimeter. And Coulomb is where the only electrical constant we know fundamental comes in the ampere. Now you look into something, look into the electrical units. Only quantity there is ampere. And they have only kilogram mass second, kilogram mass second. There is nothing. And you see that how can it happen? Actually, there's nothing wrong in that. But everything really comes from power. If you look into watt is kilogram meter square second to the power of minus 3. Now, if volt into ampere is power, right? So then immediately if I take the ampere in the denominator, I get a volt. And Tesla, how is Tesla defined? Tesla is defined as is a uniform magnetic field which on a 1 meter wire carrying a current of 1 ampere produces 1 Newton. So I can translate that. So I have 1 Newton, so I have a Newton over here, I bring the Newton over here, and this Newton I then divided it by the length meter, I immediately get per unit current I get over here. So immediately I can convert everything into these fundamental units. And Weber we know is divided by a meter square. And our ohm? Ohm is same. I square R is watt. So I take the watt and divide it by ampere square. I get the unit of resistance. So what we call ohm is an anti-unit, but at the ohm is embedded all these physical constants. Those who may be interested to play around with this, you see that not almost all physical constants really derive from 7 base units. Now, what happens is that, like Rome was not built in a day, precision and measurement are not every day. That it's not that I come to the lab in the morning, go for a cup of coffee, come back after the coffee, do my measurement and get high precision. No. Does it happen that it takes decades of measurement for the precision thing? Like when you have this kind of numbers, but you know the light velocity 200 years back was the first measurement, or 300 years back. Over the years, the velocity of light improved, and this current number came only 7 or 8 years back. So, like things have really, it's not a routine measurement. Just an example, the Montefiore constant which came after the discovery of quantum warfare. The first official measurement started in 1986. Final adopted value 2017. So how many years? 21 years it took. Take Josephson constant. It was discovered in 62. First measurement in 62. Code data first value came in 73. Final adopted value 26. So it's a long way of measurement that gives quantities. Now, Dr. Sandeep Bugre told me that I should pitch in bit on uncertainty and accuracy. There's a word called uncertainty budget. We really don't care about people who do measurements. Uncertainty budget tells me that before I start my measurement, I know all the sources of uncertainty. That's very important. It's not that after measurement I start finding by taking one double away, nothing like that. And that is when you do a precision measurement, you should know these are the sources of uncertainty, and I should know them. So that is all it came from there. So if this is the real reference value, the deviation from that is essentially your accuracy. That is what you call the accuracy. And then I have the if I do around that, if I do a lot of measurement, I get the distributionary values, which is essentially random, and that is where I get my precision. And there's a simple example, but may not be correct, by which I can kind of exemplify this. I took from the net. And this is, suppose I am hitting a board with bullets. So I have the 4 bullet marks. They are accurate because I am very close to the center, but my precision is not good. They are kind of scattered. But in this case, my accuracy is low, for I'm away from the center. But I have done the same mistake repeated times. That is why precision is high. So it's a nice example to show. And of course, that we all know that when we are taught about these things. But this is a fantastic book. Those who are interested in the subject, they can read it. And it's a very fundamental book and really explains it how one should do it. We know the random error, that is the statistical error. I do know the systematic error, or I know that my voltmeter at the 3rd digit it has a problem, or the 4th digit there is a problem. There is a systematic error. Or I know the line width is not of the slit in my X-ray or my spectrometer is not exactly what it shows. It's slightly different. All this goes into measurement. But starting 1980, this random and systematic has been gone. Like this exam coming to it, in physics we still teach random and systematic error. Is it not? But after 1980, it has changed. So the word is type A and type B. Type A is mostly random errors, but other factors which are affected by type B. And type B is generally systematic error, but there are other factors too. And in 1998, we prepared for an NABL the first guide to uncertainty measurement, and the people who made us are actually professors of Calcutta University Statistics Department. And that's a fantastic document to make and to understand how difficult things are. By the way, when you have 2 kinds of uncertainties, how do you know the final uncertainty? You just square and add. That is the way you get the final uncertainty. Type A, type B, or random or systematic, what you call. And then you can see that 68.3% of the data have 1 sigma. So now if you spread the value, you get 95%. And if you get 3 sigma, you get 97%. So you generally extend the uncertainty. You say that just don't get the RMS value. Multiply by 2 or 3, then you know all your measurements, that is 97% of your measurement will come with the RMS. Now sometimes if you look into various advertisements, find the word called we are 6 sigma company. What does the 6 sigma company means? It means that all the products, or at least that product that you are making, it meets the conformity test with 99.99998%. That is, the error in making it is so small, that is, all our process is so good that we are a 6 sigma. So that is the meaning of it. So when you see the 6 sigma company, you know it can. It means that they can make products reproducibly bad or reproducibly good. So that is the main thing in the lecture. Let me now come to the genesis of definition, new definition. Usually it started by James Clerk Maxwell. He first thought like the idea whether we should get these things going in a quantum way. But at the time, when Maxwell thought about it, quantum mechanics and quantum phenomena were all developed. So the 2 things really moved into center stage, the quantum constants and all these things are the Jerusalem junction discovered in 1962 and quantum all effect in 1980. And based on that, people started thinking that can we define all units based on mainly EC and H. And if you look into it today, we talk of quantum technology, quantum science. Every epoch in human history has a word coming in. 10 years back, we say quantum care. Now quantum is anything. Everything has to be quantum. Like someone was come with a quantum menu. Someone has come with a quantum vehicle or something quantum has to be there. But honestly, the science of metrology embedded quantum long time before any other subject really embedded. So come that what is the main driver of precision measurement? Of course, units. But definitely, as a physicist, I say that the better understanding of physical laws is at the heart of precision measurement. Now, one thing is that there is the Coulomb potential 1 by r, and this gives me the 1 by r square force. But if you look into it, there is actually one factor we don't care about. What we don't care about it, and this is the Yoka kind of potential, where lambda c is the Compton A of a photon. Photon, is the field particle for thing. So, but how much is the mass of photon? Now, there is an upper limit of photon mass, and that is 10 to the minus 18 eV per square, or minus 53 to minus 52 gram. So, if you put this number over here, this essentially is 0. So, e to the power 0 is 1. So, I'm very close to 1 by r. So, if I find a deviation of 1 by r in the potential, or 1 by r square in the inverse square law, I will know that what it means is that photon has a mass. So, I think maybe 100 years from now, someone will come and fix the mass of photon. This is nothing called zero in physics. There is nothing called stationary in physics. Either the gradient is up or gradient is down. So it may be small, but precision measurement find that small quantity. Okay, but my question is that another mover of precision measurement and why so much money has been spent is actually the world trade, which is at this moment at 26 plus trillion dollars. It's a huge amount of money. I cannot imagine what is trillion, but that is what it is. And this is where the job comes, what is BIPM, and which are essentially which we call the National Meteorology Lab, like NPL, that is which confers this fantastic physical industry. Now, coming to UTC, which is step-less universal coordinate, French word. UTC, you find it everywhere. You start your mobile, you find UTC, and why the UTC concept came? But actually, Earth is slowing down. 100 years, 1.7 milliseconds, not very large in the lung of Earth. We need to see this slowing down. But in the, if you take a long time scale, it is slowing down. So then it said that we should adjust the time world over. So there is the UTC concept came. So it's like an orchestra. Every day, BIPM take the time signal from all their country. Some of the country have advanced clocks and all that, but they have to send it to BIPM. BIPM then find the correct average time, sends it back. So that is the way the UTC came. And okay, now let me come to the relativity. So the definition of the second. So one thing I tell you, time is best defined by anything for the period of that object. Whether it is a pendulum or whether it is a thing, that is where it comes. At present, second is defined by the hyperfine transition of a cesium-133, and this is at 9.192 gigahertz, and this is the way I define the second. So fine definition, no problem, but let's look back. The original definitions really came from the length of the day, mean solar second. It is 186,400 means per day. Then people said that we should make it more accurate, so they took 1900 as the tropical year, from which the of that solar year, is a huge number. Someone that will take, but from 1967 onward, time is being defined by the atomic clock. It became commercially available, and since 1999, we have the laser-cooled atomic clocks, cesium fountain, which has correct 1 part in 10 to the power 15. Right? The latest clock, the second is defined correctly to about 10 to the power 15 years. So you can see that how much is the accuracy and precision we have obtained. This is how an atomic clock looks like. If you go to NPL or any such place, this is how it will look like. These models are no longer made. You can see the time 531.15. So this is coordinated to the UGC, which is coming from PIPM. Now, in very recent development has happened in the last 2 years. Now you get chip scale, it's the size of a peanut, chip scale atomic clock, and this is developed by NIST, and you can see that this is a peanut and this is the atomic clock, and the whole thing is that they will be now on board all the navigational satellites, so they have their own clocks and they will be synchronized. But let me now see this grandfather's clock. We all do that, it will go on and there will be time, wind the clock, etc., etc., etc. But all of us carry a bit of a timing element in our watches. You have never seen it, but there's a watch tuning fork in all your watches. Next time you go to change your battery, when the direct watch the thing, you don't know what it was. You find there's a 3 millimeter white cylinder, about 1 millimeter size, with the quartz section. What is the frequency of the quartz? Everything number 32.768 kilohertz, and this is exactly 2 to the power 15. So now in the watch, we have a series of 15 T flip flop. Each flip flop scales it down by a factor of 2. So at the end you get a second. So that is the way your watch keeps the time. So an amazing thing when you got to have a good oscillator. Okay. Now this is the time part. Okay. And now the atomic clock came. There's Ramsey in Harvard started the atomic clock as a measure, hydrogen measure for a long time, and then the Delmetal they took over the ion trap technique, and this is what they led them to a Nobel Prize, and this is all the atomic clocks are based on this. So this is the NIST clock. This I got from their website. It is correct to 1.7 parts in 10 per 15, and it delays to this time of 1 second in 20 million years. So if you look into the watch, it's not very clearly come out. All the lasers are here, and it is in this long tube where all the things are done. So when it contains, you have 6 lasers with laser cools. Now when you laser cool, your temperature is below microkelvin. So you know that all the transitions that you are going to do are in the ground state. So everything is now in the sitting in the ground state. So now what happens is that they slightly throw this ball of cloud through a microwave cavity, goes out a meter up and then comes down, again comes to the cavity. The cavity actually does that. It's a 9.192 gigahertz cavity. It does that transition, hyperpine transition. And then this laser, actually probe laser, looks into the photoluminescence or something coming out of it. And the detector, which then knows whether a complete transition has been made, and it gives the time signal. Actually, there are a lot of details I can go into a short talk time, but that is the way it will take. Okay. Now let me come to meter. Meter is defined very nicely. That is time duration of light which can travel in a duration of so much seconds. And you can see where it comes, but this is the velocity of light. Fine. So how it is defined? So I know that I can define second through by this quantity. So ultimately this is how it comes. So how it is done? Either it measures directly the light traveling time, or by indirectly measure the light traveling time by interferometer. So very interesting, the pulse of light comes, there's a reference signal which is created, then another signal comes from this guy. So this is a reference signal, and I measure the difference between these two by a precision clock. And when this becomes 1 second, I move it very precisely. I know that I move by a meter, and that's the way I get it. And this is the interferometer, and where Michelson interferometer, many of you have done it exactly that. So I look into the reference beam and this beam, and then I see the fringes. And generally, you can actually think is that if you have a good laser, they are done with, in this case, the laser is typically a highly stabilized helium neon laser. And if the laser is good, that means its coherent length is good. You can actually measure a meter in the unit of lambda by 2. Lambda of a helium neon laser is 635 nanometer. So you can see how much precision you are going to get. And if you look into it, stabilized laser can give you kilometer of coherence length. And the whole LIGO experiment which is coming in India for detection of gravitational wave is actually the interferometer, a 2 kilometer here and a 2 kilometer perpendicular tube. And it utilizes stabilized laser, which are typically fiber stabilized laser. And in Calcutta CDCI make this fiber stabilized laser, fiber lasers. And there are extremely important developments that has come in physics which are used in the definition of a meter. But still when you go to calibrate your meter, they will not take you to the lab and do all these things. They have still a calibrated meter. They'll compare it with that meter by the interferometric organization. Okay. Now we come to the electrical metrology. And electrical metrology generally is done by X-axis. You have volt, current, and hertz. So how does it go? Ampere I define in terms of electronic charge into hertz. This I can get from my time signal, and then if I have some device by which I can count how many electrons have gone, and that is what is now it does in single electron devices, I can get an ampere out. Then with the ampere, if I have a calibrated resistance which is calibrated against the Kolkata standard, I can get a voltage. I can also get a voltage from the Planck Constant by calculating it. So nowadays you can actually buy chips. I'll show them how the chips really look like. And this you can directly generate a voltage standard. Similarly, this is the quantum Hall standard, and you can generate a volt. So once these three units have been current, voltage, and ampere are generated, the all electrical voltage is at zero. Now, really, these started first one of the and all of us know really the Roy experiment. Actually, Milton didn't measure he didn't detect one electron. What he did is that he said that the minimum separation between two charged oil droplets is so much. So then it was interpreted at the end, this is the measurement of the quantization. So then things started moving, but charge quantization was not seen till the millennium when the really the micro making of micro devices or nano devices came into being. And this is single electron device. I'll go up in the length of the graph. They made what is like a tungsten. Tungsten, you know that there are gates. To get in one day class, it makes you want to come back, you don't allow it. Of course, we are all innovative. I can go underneath or jump on it. And in India, we often do that. But the tungsten can count how many people have gone in. So this is a meter is there. So this is the way I can count it. So let's know how it is done. This is generally this is how the device looks like. This is the active part by the two source and drain, and this is a gate by which they can create a particle of electron over here. And the particle of electron, the capacitance is so small, you get capacitance that E square by CT is actually quite large compared to temperature. Generally they use temperature in the 1 Kelvin or below, but if the square by CT is much larger than the temperature, you need a voltage to push it through the device. And one electron gets pushed through the device. So these are called the single electron transistors, and that is what is used to measure first one electron, and then in timing how many the timer through current standard and you get it. But I think really moved the whole quantum physics to metrology. One is the Josephson junction, other is the quantum origin. Actually, if we look into it, we knew about this quantity alpha. Your what is alpha? Fantastic. It is known for a long time. And the paper of quantum Hall effect didn't say that we are measuring age. He said it's a new method to measure the Einstein constant. Okay. Now, if we look into it, there's a very nice article by this gentleman. Okay. And now this is the three quantities which really come out from these experiments. And they actually describe almost all the except mole depends on these three constants. So their measurement become very important. You have unit of charge, whether of H and D, which will come from the fantastic experiments. Now let us see. After Josephson's discovery, Shapiro in Bell Lab had a fantastic paper. He said, I take the IP characteristic of a Josephson junction and irradiated that with microwave, then I get steps in the voltage. So that becomes the the real definition of a voltage. And the modern chips are available. Like this is the German equivalent of NPL, physically technische Bundeshaus in Braunschweig. They now sell the chips. It's an erbium superconductors on both sides and L2O3 insulator. And they have nearly 70,000 junctions. This is microfabricated, and this gives you a 10-volt step. So when you irradiate it with 70.7 gigahertz, you can see how sharp the see it is 10 point something, and up to fourth or fifth decibel place is the accuracy of the 10 volt. So that is the way now the voltage is defined. But again, if you take your voltmeter to NPL or something to calibrate, will they connect it to this guy? No. What they do is that they still use Western cell, mercury cadmium Western cell, or a xenon diaphragm, very highly stabilized. That's the voltage standard. So they calibrate this against the resistor junction standard, and then this is decimated. So nowadays actually you can buy for your lab. Fluke is a company, right? Fluke sells these standards. They're slightly costly, but they're good, and you can calibrate them against NPL or someplace and have it in your lab to see that your voltmeter is good. And then the other is of course the quantum Hall effect, the integer quantum Hall effect. And this is a gallium arsenide based chip, and you can see this gives you the Hall voltage, this gives the linear voltage, and you can see what you get in quantum Hall effect. You get the quantized size of the Hall voltage RH, and these are the step number. So generally, if you are within 12 Tesla or so, you get I equal to 2. You have to go to 15 Tesla, you get I equal to 1. And nowadays, and I know the value of R. The value of R is so many ohm. So it's essentially 25, a bit more than 25 kilo ohm. So what is that nowadays also you can get a chip, which is the quantum Hall chip you can buy from any of the standard labs, and you can have your and you have to of course cool down to at least 0.3 Kelvin and have a 12 Tesla magnet, and you can have your voltage standards, resistor standard setup. Okay, now we come to the word the definition of kilogram. Actually, the whole thing was held up for definition of kilogram. How kilogram can be connected? So the brilliant thing that kilograms are connected. And so I call it a mass final frontier. But essentially, it's the definition of mass, definition of kilogram in terms of standard constant like H that really held up this revolution. Once it was done, it was done. So this was the thing that we have to replace. Now India has copy number 57, and we get to calibrate against the BIP everything, periodically and all that. And this is the 1 year standard kilogram. So what happens is that why people wanted to replace it? Main problem is that when they compared measurement done in different labs over hundreds of years, they found an inconsistency coming. And how big is the inconsistency? In the range of 70 microgram over a period of a century. So now is it a big? Yes, 70 microgram for 1 kilogram is a big number, and I will tell you why it is a big number. So they wanted to remove that. This can we get to a standard based thing. So this is I skip it. So two methods were adopted at that time: Kibble balance, and one is called the Avogadro's project, where highly silicon is one material which human being knows how to make it almost defect-free. So a cylinder of silicon which is 8 centimeter and was made, and that is about 1 kilogram. So that's called the Avogadro project, and the Kibble balance came. The Kibble balance was what balance? I'll show you. It is in the name of the discoverer Kibble. So now how kilogram was defined? Kilogram is, if you look at H divided by this quantity, which is the value of H is meter square per second, or it is this quantity, which if I calculate is something to about 40, and the physical constants over here. This is the hyperfine transition C and H. Now, how does it come? A very simple exercise. For I know H is what? Joule second. It is a kilogram embedded into it. For Joule is kilogram meter per second square per second. So it is kilogram meter square per second. I know differently the definition of meter square. I know this is differential of second, just comes out. So in terms of playing around with units, perfectly alright. I know how kilogram is related to age. So let us now see how it can be experimentally realized. So you can see the result, how to see the result. This was one of the very important result which adopted this method. This is how the cubal balance in NIST in USA looks like. I'll describe this balance. And this is the IPK. And you can see that VIPM measurement was plus minus around 100 microgram. This is the Korean measurement. This is the Chinese measurement. This is the US measurement. This is the Japanese measurement. This is the Canadian measurement. This is PTB. This is the adapted value. And this is the comparison with HIP. So all this measurement you can see that it has to really came down to about plus minus 25 microgram when adapted. Now let me talk about cubal balance. This is the gentleman who discovered this balance in 75, proposed this balance, that is called watt balance. I tell you why it's called watt balance. But unfortunately, before everything was adopted and all that, it must have in 2016. So he was in NPL UK, and in his memory, this balance came. What does watt balance do? It is really high school physics. It has two things into it. Clearly left hand rule. All of you know that. I have a wire in a magnetic field carrying a current, it will generate a force. So suppose I measure the kilogram or whatever measure by that force, I can balance it. So I'm immediately converting the weight from mass to an electric current, and B into L. B is the magnetic field, L is the electric. So this is the problem. The uncertainty in B and L was very high. So how to do that? Then brilliant guys came. They said that I can use Faraday's laws of induction. I remove that mass and just let the coil go in a wizard velocity which I can use my laser into a battery and measure the voltage generated. That will be BL into B. So if I combine these two, the voltage generated and the current over here, I can then combine these two and I can define the things. Let us see now. This is actually how it is done. This is a calibrated resistance which is calibrated against a quantum Hall standard. There is resistance junction and integrating voltmeter, and the integrating voltmeter is the one it really calculates an average best. It converts into a frequency. Then over a period of time it calculates the average. And then I have a laser system by which I can see where the measurement balance comes. So my first measurement batch is MGPA line. Then my second measurement, I let it go through the velocity and measure this voltage, and then I get this done. Combine these two, I get MGPA equal to P. So it's a watt. That's why the name watt balance came. So the MGP now is converted into watt. And watt is very easy. It has voltage and current. Current is I measure it by a standard resistance. Now you can see voltage I can define by resistance constant, and this resistance I can define by a constant, our quantum Hall effect. So if I combine these two now, it's a very interesting thing. I have two frequencies, and this is the step on which I am doing the measurement of the quantum Hall. So I get MGP, but so this is actually age was determined initially from mechanical measurement by putting a standard. It's a bright idea start. They said I can measure age from other measurements, but why don't you use this age and measure a kilogram? That's why the revolution that a kilogram started getting measurement by using age. So in my opinion, this was the most brilliant thing that has happened. And there are a lot of papers available that is where this happened. Very quickly, I throw into the Avogadro project. This is how the silicon is about 8 centimeter silicon made from a highly purified silicon. And if you look into this relation, this also has an age. When age comes, see this is dimensionless, 1 by 1. This is dimensionless. This is a relative atom mass of silicon. So actually, if you look into the very simple exercise, you take the fine structure constant square and do this algebra. This is a Rydberg constant. You see, there's an extra h. So to balance that unit, you have the h coming over here. So again, h comes over here and gets irritated to the mass. So why silicon? the defect density is so much low. So it's an art to make it. It is not very easy that I get a hunk of silicon and sit and make no. It takes years to make it, and they made some 70 or 80 test pieces, and 2 or 3 pieces ultimately go into the test. Okay. Now, why do I need the last part I coming in? Why do I need the precision measurements? What the big thing? So, if you look into it, in the best metrology lab, I am measuring massive 25% of 9. But then when I actually come to the market through a metrology system, you have seen this Dharam Carter, right? If you go to the Dharam Carter, I don't know what is Dharam into it. But this guy is saying I'm doing Dharam. From the very beginning, he's maybe saying that. But in a best Dharam bridge and ton bridge can be 1%. And is there a good thing or bad thing? You look into it. What is this 1% of the error? Country produces 320 million tons of food. Rice is produced 150 million ton rice. Wholesale price of rice, the ordinary rice is 30 to 40,000 per ton, whereas basmati goes to 70,000 per ton. Now, just simple calculation. If you have 1 million ton and I have 1 part in 10 to the 3 error, then 1,000 ton is my error, and converted price is 45,000 error. So you can imagine error in 1 part in 10 to the 3 was 45,000 error. Now, this is only 1.1% of the total rice trade in the country. It's an amazing number. So it's a large number. Why do you need precision measurement? Time. For all your air traffic controller depends on precision. But if all the altitude, everything related to precision timing. If the time goes back, you are off. And space travel. How do I know the satellite is in a certain distance? I send the signal, send the reflected signal coming back, multiplied by C, and I get the time. So time is very important. Okay. Now let me come to the last part. That is, we have talked of trade, that is certificates and all that, and let us then see where the certificate comes in. So I have outsourced my product. Now everything is outsourced today. So no one makes it in-house. So like how do I get it into science, into the domain of commerce? And this is exactly something very important for the country. The agricultural products in this country are routinely rejected by some of the advanced countries. Many pesticide residues. Still, there is no foolproof method to calibrate, measuring, and calibrating and meet international standards. So, those who are doing chemistry research, this is a very important thing. How do I measure it? Okay. So, let us now just see. Let me just keep it. Now, let us see that I have 3 manufacturers, and with loss of generality, I can call them Omar and Akbar. Now, Omar and Akbar, one of them makes radiator, one of them makes seats, and this is a little soon for and then Anthony is a bit, ambitious. He makes it not only for Suzuki, he makes it for he makes display in a car. It's a very important thing. So how do I then see that what I make is compatible? So I have to go to the apex standard of NPL. Can all of them run to NPL get their standards measurement check? No. So they go through series of calibration test labs, and they are accredited through NABL. Then you can trust their certificate that it is correct. So that is where it comes. Now, in the country, if you are doing it, no problem. But then problem comes, Anthony is ambitious, sends it to Ford in Mexico. So whatever testing in calibration it does is not only done by NPL. NPL as standard should have been traceable to PI. Only then it will be accepted in Mexico or European Union or whatever. So that is where the full laboratory accreditation process comes. So let's see now the last part. This is called metrology pyramid. So you have the international calibration laboratory, PIP, national lab. You have a chain of calibration labs which you really need to the ground scale at the shop level. So that is the way the whole calibration and accreditation process works, and it depends on 3 things. One is the meter convention which is signed, then MRA signed in 1999 October 14, and then creation of NABL or the Quality Council of India. These 3 things really are the 3 important milestones which gives us this freedom. So it was actually the country became independent in 47, and thanks to these forefathers, they immediately decided that we come out of the British system and get the metric system. It was adopted by the Parliament in 1957, and then the Meter Convention was signed by the K.S. Krishnan, one of the greatest scientists the country had, and we signed it, and then got all the documents for BIPM. That stage started India as a modern nation with field of metrology. Well, I don't know whether anyone has seen a photopost in his life. Putakadi in his life? No, I have seen it. But we grew up before 1960. 1960, the country decided that we go metric. So even our Taka Anna Pai, which is the old system, was replaced by Noya Paisha. So this is the photo paisha of that time. You go to Amazon, you can buy 4 photo paisha for 230 rupees. I don't know if it's worth it, but you can still buy it. But photo paisha was a very important thing. As children used to collect them, for 1 photo paisha used to give you 2 candies. Okay. Now you come to Noya Paisha, you get 1 paisha, these things you don't see it anymore. They are also obsolete. This I took it from Amazon. Amazon says the whole Purono Noya Paisha for 490 rupees. If you have old paise, there are people who can buy it for a lot of money and give it to them. So there, okay. Now the second one, last one, important document was I was fortunate enough to sign it on behalf of the country, and then the mutual recognition agreement. What it says is that all the national labs, their standards will be followed. But is it that I declare that it will be recognized? No, there's a method. But the fallout is that if test certificate issued in India could be adopted in European India or USA or UK. So if I am a manufacturer, I don't have to go to each country and get a test certificate. So this saving he has. So but the scope for MRA is very challenging for us and to implement it. So NPL has to be completely recognized internationally, accredited by it has to change the standard building to Apex standard building and all that. And ultimately in 2007, we were allowed to use though we signed it in 1999, it was allowed to use the logo in 2007. Anyway, so where does the NABL come? Well, we have an unbroken chain of calibration, accreditation laboratory, and that's the NABL. It's located somewhere in Haryana. It started as a project in 1983, and then it became registered as a society. It makes sure that you have auditors, testing, laboratory, all this laboratory has to give you the calibration or test certificate will be accredited, and they make sure that everything is traceable to NPL. And NPL has to make sure that it is traceable to the international standard. Just a second before I stop. Actually, opening an accredited standard laboratory or calibration laboratory is not a very high thing. You don't have to be laser cool clock or anything. I can open a calibration lab just with a meter stick and a clean room and a guide measuring. Only thing what I have to do, I state my precision or accuracy or my error. I say that I can measure a meter with a precision of plus minus 0.5 mm. So I'll be accredited only in that statement, nothing more than that. So if I now start giving a test certificate with a precision of plus minus 0.25 mm, I'll be immediately caught that you are giving a certificate for which you are not accredited. A word of caution. Many of the pathological labs, may not be accredited for all the quantities and they don't follow procedure. When you go to check your blood, do you wear a glove? Many places they do, many places they don't wear a glove. But wearing a glove is a part of their procedure. So once I told, I go every 3 months to check my blood. They say, nah, folding, glove, I'll complain it to NPL. Everyone started running, they found a glove, came around that, like, so you can give a fair element. They give a fair element, things start moving. Anyway, that is just, I'm telling you, many of the labs are not accredited in all the quantities. You can ask them. They're supposed to display with the certificate that I have accredited. If they don't know, so there's a problem. Anyway, NABL has come to stay with us. It is now with the Department of Commerce and is a very important organization which is really helping the world trade. Just a quick thing, we have a total number of accredited laboratories in the country now. This is 2-year-old data. And this is the total number of calibration labs. You can see one thing. The highest number of labs are in 4 states. Gujarat, highest in Maharashtra, then Karnataka. And look at this axis. This is the manufacturing axis of India. The largest concentration of manufacturing industry, including car manufacturers, are in these states. Particularly Tamil Nadu. Tamil Nadu has the maximum manufacturers of cars and ancillaries of cars. And you see the effect of it. IIT Madras has a technology incubator. Just did a message. I got news. There are 500 startups in their incubator at this moment, and they raised 53,000 crore of rupees startups. So you can see how intense these activities are now in the country. And this is gives you the number of pathological labs. Bengal has a large number of pathological labs. Anyone can place this in? For our doctors, unnecessary assessment, a lot of unnecessary tests. So this is a big business. See, you have a pain in your leg, they said to you, do all the tests in your hospital, tuberculosis and all this kind of thing. So this is where the calibration labs. Wow. So the Bengal has one of the largest number of pathological calibration labs. So we have covered this story. I don't know whether I have covered it correctly or incorrectly, but I tried to cover it. And then I just want to say that it is a big endeavor, scientifically, monetarily. Think quantum, think contribution, and think contribution. Thank you. Story. I don't know whether I have covered it correctly or incorrectly, but I tried to cover it.
There's one comment in
I
the
just
chat
want
box.
to say that it is a big endeavor, scientifically, monetarily. Think quantum, think contribution.
Oh, Shiruguri.
Yeah.
Bolo Shiruguri.
Can you see the question? Any
Yes, yes,
story
yes.
on the
I don't know whether
No, I cannot comment that, but one thing is that
I tried to cover
one
the mass of
comment in
progress
the
is very
box.
important.
Yeah,
Like
I
over scientifically, monetarily, or they are very important.
Oh, Shiruguri.
They are very important.
Bolo Shiruguri.
Not only for the point of view, but from the basic physics.
Yes, yes, yes.
I don't know.
No, I cannot comment that, but one thing is
I
that
tried to cover
one
the mass of
comment in
progress
the
is very
box.
important.
I
Like over scientifically, monetarily, or they are very important.
Oh, Shiruguri.
They are very
Online.
important.
Bolo Shiruguri.
Not only from the point of view, but from the basic physics.
Yes, yes, yes.
I don't know.
No, I cannot comment that, but one thing is
I
that
tried to cover
one
the mass of progress is very important. Like over scientifically, monetarily, or they are very important.
Oh, Shiruguri.
They are very online.
Bolo Shiruguri.
I think this standard basic change.
Yes, yes, yes. No, I cannot comment that, but one thing is that
one mass of progress is very important. Standard is still reliable. Only thing that they may upgrade their primary standard.
Oh, Shiruguri. Bolo Shiruguri.
I think this standard basic change.
Yes, yes, yes. No, I cannot comment that, but one thing is that
one mass of progress is very important. Standard is still reliable. Only thing that they may upgrade their primary standard.
Oh, Shiruguri. Bolo Shiruguri.
I think this standard basic change.
Yes, yes, yes. No, I cannot comment that, but one thing is that
Years back is what is talked about Dennis Wilkinson from Oxford.
Oh, Shiruguri. Bolo Shiruguri.
Are we here by chance? And he spoke about physical science and said that certain changes or deviations against
No, I cannot comment that,
make us
but
not
one
exist.
thing is that
So this procedure measured around 20 years back is what is talked about Dennis Wilkinson from Oxford.
Oh, Shiruguri. Bolo Shiruguri.
Are we here by chance? And he spoke about physical science and said that certain changes or deviations against
No, I cannot comment that,
make us
but
not
one
exist.
thing is that
So this procedure measured around 20 years back is what is talked about Dennis Wilkinson from Oxford. Said that certain changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing forces. Said that certain changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing forces. Said that certain changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against no, I cannot comment that. Make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against
no, I cannot comment that.
make us non-existent. This procedure we had around 20 years back is processing Said that changes or deviations against no, I cannot comment that. Make us non-existent. This procedure we had around 20 years back is processing